We now discuss the solution of a problem from the section Linear Algebra. The problem is based on matrices and the related rank and the determinant. This problem has appeared in CSIR National Eligibility Test held on 30th November 2020 and it is from the section B. Let capital A be an n by n matrix of rank 1. Let alpha is equal to determinant of I plus A, where I is the identity matrix, and let beta is equal to trace of A. Then which of the following is true? The four options are given to us. Option 1, beta minus alpha is equal to 1. Option 2, alpha minus beta is equal to 1. Option 3, alpha less than beta plus 1. Option 4, alpha greater than beta plus 1. This is the problem given to us. Now, let us eliminate some of the options by giving a counter example. Let A be a matrix of order 1. Let capital A is equal to a 1 by 1 matrix whose entry is C. Here C not equal to 0 because the rank of A is equal to 1. Now beta is equal to trace of A, and A is a 1 by 1 matrix whose entry is C. Therefore, trace of A is equal to C. Now, alpha is equal to determinant of I plus A. I is a 1 by 1 matrix and A is a 1 by 1 matrix. Then the I plus A is the 1 by 1 matrix 1 plus C, and its determinant is 1 plus C. So this implies alpha is equal to 1 plus C, where C is equal to trace of A is equal to beta. Therefore, alpha is equal to 1 plus C is equal to 1 plus beta, and which will give rise to alpha minus beta is equal to 1, and which is the option 2. And the option 1, option 3, option 4 are not true. So thus the options 1, 3 and 4 are not true, and it appears and option 2 is true. In the examination, what we say is these 3 are not true, therefore this is true, and we will tick the 2 and there ends the matter. Our answer is the option 2 is true. This is as far as examination is concerned. But we ask, what is the proof of this alpha minus beta is equal to 1 in a general situation when A is an n by n matrix. I want to give you a proof of that in a general setup. So that we will do in the next subsequent slides. So this is the theorem now. Let A be an n by n matrix of rank 1. Let alpha is equal to determinant of I plus A, where I is the n by n identity matrix. Let beta is equal to trace of A. Then we want to prove alpha minus beta is equal to 1. So to prove this result, we require 2 results. The first result is the following. Result 1. The sum of the products of the eigenvalues taken I at a time, sum of the products of eigenvalues taken I at a time is equal to sum of all ith principal minors. What do you mean by a principal minor? So MII will denote ith principal minor. What is ith principal minor? It is the determinant obtained by omitting the ith row and ith column of A. And SI denotes sigma all ith principal minors, the sum of all ith principal minors, that is equal to sigma I is equal to 1 to n. Now, the result is Si is equal to the sum of the products of eigenvalues taken I at a time, and that is equal to the sum of all ith principal minors, and that is equal to sigma I is equal to 1 to n. This is the result what we require, and this is the first result, and we want the another result that we will see now. Result 2. Let A be an n by n matrix if lambda 1, lambda 2, lambda n are eigenvalues of A, then determinant of I plus A is equal to 1 plus lambda 1 multiplied by 1 plus lambda 2 multiplied by etc. 1 plus lambda n. And this is equal to 1 plus trace of the matrix A plus sigma m22, the sum of all 2 by 2 minors, plus sigma m33, the sum of all 3 by 3 minors, plus so on and so forth. At the end, the sum of all n by n minors, and there will be only n by n minor because it's of order n. So that will be determinant of A. So this is the result what we require, and I will prove this result. Proof. We have the characteristic polynomial of the given n by n matrix A is determinant of lambda I minus A, that is equal to lambda minus lambda 1 multiplied by lambda minus lambda 2 multiplied by lambda minus lambda n. This is the characteristic polynomial after factorization. Now put lambda is equal to minus 1. Why are we doing? And we want determinant of I plus A to get that one. So put lambda is equal to minus 1 in the above, then determinant of minus I minus A is equal to minus 1 minus lambda 1 into minus 1 minus lambda 2 etc. minus 1 minus lambda n. Now take a minus 1 common. So that will be determinant of minus 1 times of I plus A. And from this minus 1 taken common, minus 1 times of 1 plus lambda 1. Similarly from here, minus 1 times 1 plus lambda 2. Here from here, minus 1 times 1 plus lambda n. So this will be determinant of minus 1 times I plus A, minus 1 times of 1 plus lambda 1, minus 1 times of 1 plus lambda 2, etc. minus 1 times of 1 plus lambda n. Now, let this minus 1 come out of the determinant, and I plus A is a matrix of order n, and from this determinant, if minus 1 wants to come out, and it will come out as minus 1 to the power of n into determinant of I plus A. And minus 1, minus 1, minus 1 n times minus 1 to the power of n, and the product of the factors here. So that is, and now cancel off minus 1 to the power of n on both sides, you will get that the first result. That is, determinant of I plus A is equal to 1 plus lambda 1 into 1 plus lambda 2 into etc. 1 plus lambda n. That's our first result. Now multiply this, and this will be 1 plus the sum of all eigenvalues lambda I plus the sum of all eigenvalues, the products of eigenvalues taken 2 at a time, plus sigma taken 3 at a time, plus etc. all at a time. So that will be 1 plus the sigma I is equal to 1 to n lambda I, sigma I not equal to j lambda I lambda j, that is the sum of the products of eigenvalues taken 2 at a time, sum of the products of eigenvalues taken 3 at a time, taken all at a time. and that will be 1 plus the sum of all eigenvalues is trace of A, and this is S2, and this is S3, and this is Sn, but that will be determinant of A. And we have 1 plus trace of A plus S2 is sigma M22 plus S3 is sigma M33 plus etc. determinant of A, and this we are writing and from the earlier slide. So this is the result what we have. So thus I have proved the result what I have stated, and I will now use and prove that general result. And this is the theorem now for us, and solution. By result 1 we have determinant of I plus A is equal to 1 plus trace of A. It is result 2. By result 2 we have determinant of I plus A is equal to 1 plus trace of A plus sigma M22 plus sigma M33 plus sigma MNN is in fact determinant of A. And because the matrix capital A is of rank 1, then all the ith minors I greater than 1 are 0. This is 0, this is 0, this is 0. All of them will become 0. Since I is of rank 1, all its ith principal minors I greater than 1 are 0, and hence this is M22 is 0, M33 is 0, determinant of 0, and their sigma is 0. So that is the one. Therefore, each MII is 0 for I greater than 1. Then the above equation 1 now becomes determinant of I plus A is equal to 1 plus trace of A. And so determinant of I plus A is alpha, trace is beta, substitute. Alpha is equal to determinant of I plus A is equal to 1 plus trace of A is equal to 1 plus beta, because trace of A is beta. Now this will imply alpha minus beta is equal to 1, hence the result. Thus we have proved the general result in a general setup. So that is the result, and that is the proof of that result. And I am sure that you have understood the solution of the problem and the proof of the theorem stated in a general setup, and work out some more problems on these lines. And I wish you all the best. Thank you.